but let's see here. I handed out, and I just made it available on our Moodle page as well. But for everyone in class, fresh today, set of tables, same thing as the formula sheets. You'll get a fresh copy, but it'll look like this on the tests. Okay, so we need to learn how to use this table, and we'll do that today. So far 2 handouts, formula sheet from last week, set of tables. You need copies, they're up here. And I posted, so the formula sheet is on Moodle as well, under the course material and the tables. Now I'm going to repost this because we're not going to use this first table. It's called the Z table, but I'm going to be cool, or I guess I declare I am cool by using just table C, which is called the T table, which is the copy that you have. So it'll be the 3rd page if you're looking at the tables on Moodle, but I'll repost it with just the table that we're using. But it might be nice to see, both. Okay. All right. Another thing I wanted to note, I thought putting it on Moodle would be enough, but and I realized it might be nice to know when your test is. And I mentioned it last week, but test number 1 is on October 10th, right? And so it'll be on chapters 1 through 4. And then after that, we get into the really fun stuff. And so I can't wait. But,
in progress.
Oi. How do I? Okay. I'll just, for good measure, just mute everyone. Need to change that setting. Anyways, whatever. So, some housekeeping. So last week we finished chapter 3. We were talking about random variables. We did those fun examples with the gambling where there's some payout for certain outcomes and we attach the probabilities to those. But we're going to start fresh today with chapter 4, which is called Distributions of Random Variables. Yeah.
Are you able to upload it to the Moodle? Just because I go along with you in PowerPoint, we can send you something.
Which one? This.
Yeah, it's on the front.
Oh, should be there. Under the slides, there's chapter 4, and is it not? No, it's there.
Oh, yes, it is. Thank you.
No problem. That was easy. There. So they're just in the slides. I did remove 3 of the slides because they were kind of extra, but I'll try to point those out. But okay, good. So today we're going to do section 4.1, which is on the normal distribution. We already kind of know what that is, but we're going to learn kind of the anatomy of the normal distribution today. Okay, and just how do we find things like probabilities associated with the normal distribution, which is going to haunt us throughout the rest of the course. And so even if it doesn't make sense today, we'll keep working at it and we'll see these similar types of problems throughout the rest of the course. And so we will get really comfortable with it. But this is our first day, so just go easy on yourself. Okay. All right. And then whenever it says brief on Moodle, I'll just kind of do a 1 sentence thing and move on, kind of touch on it, but I'm not going to test you on it or anything like that. It's just, you can read it on your own if you want, but we're going to focus on the binomial and the test 1 outline next day. Okay, good. Any questions before we start? Yeah.
So I know it says it's till 4.5, like where we stop on Tuesday. So is only half the chapter chapter 4 on the test?
So whatever we get to, here, I'll pull up just so I can, well, I can't point, I'll point physically here. So definitely 4.1 and 4.3 will be on the test. Okay, but usually what I do, because we introduce the Poisson, which is also kind of a biggie, what I'll do is I'll have a bonus question on the Poisson, because you'll have seen it, but we haven't had, a whole weekend to work on it and stuff like that. And so, so I'll give you a bonus question where you can show off that, hey, I actually learned the Poisson. But if you don't have time to cover that, then that's totally fine. And so it will be, 1 through 4, but the later part will be less emphasized.
Will there be more assignments based off chapter 4 due before the test?
So, okay, so it gets tricky because I don't want to have them due before the test. The one today can be due before the test. I give you a week, but gets a little tight, right? The binomial would be due midnight, the night of the test. So, but it might be a good idea to do them even before the due date, but I do make them open for longer. Unless you prefer to have that hard deadline, because you should do it before, but usually you can self-impose that hard deadline of before the test, because you should be using them to study for the test. But I go beyond the test. Okay. Good. So for emphasis, section 4.1 and section 4.3 are going to be the major players from chapter 4 on the test. Okay, and so here we go. 4.1 is the normal distribution. So we've already seen the normal distribution way back in chapter 1, I want to say. We know that it's unimodal, so it has one peak, it's symmetric, and it is also bell-shaped, right? It's got this kind of bell-shaped distribution. Now here, I do want to make a note. The normal distribution, usually I capitalize normal. Obviously, in this case, it would be capitalized anyways, but I do want to make a note. You don't have to capitalize it, but I capitalize it to emphasize that it's a name, right? And so a normal distribution is the name of a shape. So normal is the name of the shape. If you want to be fancy, you could call it the Gaussian distribution, but we don't. We call it the normal distribution. And so just like if I draw these shapes, you can name those shapes, right? Triangle, circle, rectangle, square, blah, 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 blah. Now we have a new shape, kind of a normal distribution. This wasn't a very beautiful example of it, but they're kind of hard to draw, so just do your best. What's kind of fun is there are a lot of things that we could measure. Now we're on a continuous scale, right? When we're measuring for the normal distribution. And so a lot of things follow a normal distribution. And so that's where we're starting, is because a lot of things follow a normal distribution. And so the problem is that none are exactly normal, but we'll kind of ignore that. Some shorthand notation that we're going to use is this capital N, which is the name of the shape, right? Normal. And then with a mean mu and a standard deviation sigma. Okay. And so here, we're going to read this read as a normal distribution with a mean mu and standard deviation sigma. So it's really just shorthand for what? We've seen it before. Shape, center, spread. What? But that's all you need to describe a distribution. I know, right? Cool. So now we've got this shorthand. This is the shape and the center and the spread, right? Describing the entire distribution. Okay. So those are all the things that we need to know to describe a distribution. And in this case, it describes a normal distribution. We're going to introduce a couple more distributions, but the normal one is the one we're going to work with the most. So shape, center, spread, then you've described this entire distribution. And so we develop this shorthand. In fact, often what we do is we write X, so some random variable X, which is going to be a capital X, and I'll clarify that there. Capital X, a little tilde, which you're going to read as follows up. So here, this is, well, one, it's a tilde, but you're going to read it as follows. Normal distribution with a mean mu and a standard deviation sigma. So X follows a normal distribution with a mean mu and a standard deviation sigma is how you would read that. Okay. So that shorthand condenses that blurb quite a bit, right? Now, we've got the shape, normal, right? And so it's drawn on here nicely already. The center mu is here. And then there's no physical thing on here that I'm going to attach my sigma, but usually I just kind of write it down below, sigma equals 3 or something like that, right? The spread is 3. And we'll talk more about that in a bit, but I'll remove the equals 3 and just kind of write sigma below the distribution somewhere. So X can be anything that you have measured, right? So anything that follows a normal distribution. One example is heights. This one's pretty funny. Does OkCupid still exist? I don't know. Probably not. So I think it's extra funny that there's a yoink here. Yoink. Anyways, heights follow a normal distribution. And so we know that, okay, if I know the average height of some population, right? Usually we don't, we kind of separate by genders just because we know that if we merge the two, then the average height wouldn't tell us very much about either group, right? And so then we talk about the average height of males and females separately because women tend to be shorter, obviously. But there's variability there, right? And so if we know the average height of males, for example, then, right, I think this is the true US distribution, the faint purple line here. We'll talk about that one. And then there's kind of, they've done a lot of work here, but the heights that are on OkCupid, which is a dating website, in case that's not obvious. But anyways, we've got the heights of males in this case. We know that, okay, the average male height is, let's see, does it, oh, it doesn't say what the average height is, but it looks like it's like maybe 5'9" or something, 5'8", 5'9". Doesn't matter. Knowing that, and knowing that it follows a normal distribution, right? That's just saying that, okay, we expect most males to be hovering around those heights. We know that there are some that are shorter and some that are taller, right? But there are fewer of those extremes, right? As you move into the extremes, you expect fewer and fewer and fewer of them, right? And so we don't need to worry about this example, but it is a kind of a funny example. And so here, especially on a dating website, I guess, because what would you expect? People on dating websites aren't just taller. That's not a thing. They're from the general population. And so you would expect, if they were kind of being truthful, that they should follow the same US population distribution. What they're finding is they don't, but they do though, right? Probably, most likely. And so then the whole curve's been shifted over a little bit. Okay. So same thing happened with females, which is also kind of interesting. Everyone just wants to be taller, but more boring but useful is this slide. So we've got a mean and a standard deviation of the population, right? Mu and sigma, because remember, when we have Greek letters, those are from the population, meaning measurements from the population, we call those parameters, right? Just as a little refresher from, I want to say, the first class that we did. Right. So, oh, I wrote parameter again. Nope. The two P's go together though, population, right? Measurements from the population is a parameter. So to get a handle on what these things look like, notice the shape is the same for both of these distributions, right? They're both normal, so they both have the same shape. Okay. The center for the first one is 0. Oops. I shifted it over a little bit. And the center for the second one is 19, which means we've just taken the same shape and we've shifted it over to 19. Okay. Now, the spread of 1, so the standard deviation of 1 in the first one versus the standard deviation of 4 on the second distribution, those look the same, right? But if we do some sleuthing here, looks like, okay, I've got a -3 to 3, which is kind of leading us down the path of, okay, looks like I can fit about 3 standard deviations on either side of the mean until I kind of run out of space, but we'll talk more about that. But just now you've seen it a little bit. 3 standard deviations, right? If sigma is 4, right, then I would have to go 19 and then down 3 standard deviations-ish. Now I'm between 7 and 31, right? And so I have a bigger spread than I did when sigma was 1. And so that's what the standard deviation is telling me. It's telling me the spread. Now, these only look the same because I'm just looking at one of them at a time, right? However, if we put the two on the same kind of same scale, right? What would these two look like? The first one is centered on 0. So that's this little guy with sigma equal to 1. And the second one is centered on 19 with a spread of 4. So when they're on the same scale, now the spread of 4 is kind of taking up more space, right? So it's a little bit flatter and a little bit wider, right? More variability. Okay. And so here, more variability. Yeah. I'm trying not to get ahead of myself. I have a lot to say about the normal distribution, but we're just building up some skills. Okay, so how are we going to use the normal distribution, but also kind of any distribution? Here's an example. If we have SAT scores and we know that they're distributed nearly normally, right? Everyone's kind of hovering around the average score, and then there are some kind of lower scores, but they're pretty rare. And then there are some very high scores, but they're also very rare, right? And so kind of the rarer, the more extreme we get, right? And so we know that SAT scores, and this is an American example, obviously, because we don't have the SATs and the ACTs, but they're just two kind of entrance exams that you can write in the States. And they're supposed to measure kind of similar things, academic ability, I guess. And the difference is that the SATs have a mean of 1,500. So the average score on the SATs is 1,500 with a standard deviation of 300, right? Quite a large spread. Whereas ACT scores are still distributed nearly normally with a mean of 21. So all of a sudden you've got a score of 21 on average with a spread of 5, right? So those two, as it stands, you can't compare those two, right? But we can. A college admissions officer wants to determine which of the two applicants scored better on their standardized test, right? And so the SATs and the ACTs are standardized tests with respect to the other test takers, right? So among their group, so Pam, who earned an 1,800 on her SATs, or Jim, who scored a 24 on his ACT exam. What would you do to compare these? Just kind of dissecting your problem solving skills a little bit, right? So we know that the SAT scores, so Pam wrote the SATs and Jim wrote the ACTs. The SATs, there's a line there, but it's so faint, are centered on 1,500, and the ACTs, I'll match their color scheme, I guess. Nope. There's even a line I can follow, but I couldn't do it. There. Just looking at this, knowing that the center is 1,500 and then the center is 21, just looking at these graphs, right? It looks to me like Pam is further from the mean than Jim is, right? But how can I communicate that? We have the standard deviation. That might be nice, right? What if we said, okay, well, I can figure out how many standard deviations Pam is from the mean, right? And how many standard deviations Jim is from his mean, right? And so let me see if I have, I'll add a page here. Oh, and I need, how do I? I can never remember how to add. Oh, well, add lines. I wish I could. Okay. So to solve this problem, we can find how many standard deviations, which I'm going to abbreviate SDs. We can find how many standard deviations each score is away from the mean. I'll say their respective mean. So if we focus on Pam, we're looking at this. Let me see if I can grab just a copy. Oops. Copy pasta. Make it little. Score of 1800 with a spread of, I want to say 300. So the distance between 1800 and 1500, right, is, so Pam's score, oops, SOAR. Can't spell today. If I go 1800 minus the mean, right, the distance from the mean, but then taking into account the standard deviation, I'm going to go for 1, right? 300 divided by 300 is 1, which means that we can communicate that by saying, okay, Pam's score is 1 standard deviation above the mean. Therefore, Pam's score is 1 standard deviation above the mean. Can do the same thing for Jim. Who scored 24, which is not obvious from the graph or the image. So now drawing in red is pretty jarring, so I'll do green. So Jim's score is at 24, we were told, and the spread was 5. Sigma is 5. So Jim's score of 24 is 3 units above the mean, but divided by 5 means what? 3 over 5. And I'm admittedly going to check 24 minus 21 is 3. Okay, phew. Divide by 5. I get, I'll just do the 0.6. Because it's easier to talk about. which means what? It means that Jim's score is 0.6 standard deviations above the mean. Yeah. So therefore, Jim's score is 0.6 standard deviations above the mean. Would you rather be 1 standard deviation above the mean or 0.6 standard deviations above the mean? Probably 1, right? Because it's a better score in comparison, right? And so therefore, Pam's score, what was the question? Therefore, Pam scored better than Jim, right? Relative to their group. So what we did here is called standardizing, right? We can take a measurement, and as long as we know the center and the spread, then we can standardize it to be talking about, okay, how many standard deviations above or below the mean is this thing, right? And so here I'll do a line, right? So what we just did is called standardizing. We have to dissect what we did here. We did the same thing in both scenarios, but first we found the distance from the mean, right? And then we divided by the standard deviation, right? And so it's the distance from the mean divided by the standard deviation. And this gives us a standardized score or standardized value, let's call it. What if our value was, oh, was there a question or? Oh, yeah. This one? Nice, 1800. What if Pam's score was not above the mean, but below the mean? Be tempting to do 1500 minus 1200 to get a positive value, but then we lose that knowledge that it's below. And so in order to always have negative values below the mean and positive values above the mean, because then that tells us something as well, right? Then what we do is we take the score that we're interested in, right? And we subtract the mean, right? If that score that we're interested in is larger than the mean, I get a positive value. And if that score that I'm interested in is below the mean and I subtract the mean, I get a negative value, right? So there's information in there as well. And so what we do is we take x minus mu divided by sigma, where x is the value we want to standardize. I'll also write a note here. Notice if x is less than mu, x minus mu is negative. And of course, if x is greater than mu, x minus mu is positive. You would have developed this given enough time and kind of sitting down and having to compare these two scores, you would have gotten here, right? And so which is cool, right? But now we're going to call it a Z-score, and we're going to call it a standardized value. But just remember that you would have got there eventually on your own, right? And so this is a standardized value, and we are going to be standardizing with Z-scores. So Z-scores are those standardized values. Now I'm just gonna put it on here right away. Z is X minus mu over sigma, which is also on your formula sheet. Let's pop in there for a sec here. We did discrete random variables briefly last day, or all day last day, I guess. But now we're in the next section, which is the normal distribution section. And now we know what this means, right? And so I'll copy this in here because it's on your formula sheet. So it's nice to have it. I'm just going to put it here, put her there. We'll just talk through this example, but we already did it. So that's why I'm going to float through it a little bit. So what we did, right, is we found that Pam's score was 1 standard deviation above the mean, and Jim's score was 0.6 standard deviations above the mean. So if we put them on the same scale, right, that scale is going to be centered on 0. And as a rule, the standard deviation is 1. So then we can translate, okay, if Jim is 0.6 standard deviations away, then he's closer to the mean than Pam is, who's 1 standard deviation away. Okay. So we're going to be talking about the number of standard deviations away from the mean. Okay. So these are called standardized scores, or Z-scores is what we'll call them. And we kind of got there intuitively, right? The Z-score of an observation, and that observation is denoted by X. And the Z-score of X is the number of standard deviations it falls above or below the mean. And so this is what we did, right? We took the score, found how far it was from the mean, took into account the spread, all good. Now Z-scores, you can standardize any distribution or values from any distribution, but we're going to focus on Z-scores for normal distributions, but we can do them for any distribution. Now, before we get ahead of ourselves here, I'm going to add a page and sneak this down here. Okay. Something that we're going to really cling to is that observations that are more than 2 standard deviations away from the mean, so in either direction, are usually considered unusual, right? And so I'm going to highlight that because what we're going to find is statistics, we don't really care about, run of the mill, everyone's doing this, right? We care about those unusual observations, right? Have I found something extreme, right? And so are the results of this new medicine that I've developed unusual compared to, well, hopefully in a good way, right? Are they significantly better than the other medicines that are available, for example, right? And so as a rule of thumb, anything that's more than 2 standard deviations away from the mean will be considered unusual. And so what does that look like? Z is centered on 0, -1, -2, +1, +2. This is Z. I can't resist. We haven't seen it yet, but usually we go 3 standard deviations on either side of the mean. And then we've captured, spoiler alert, 99.7% of the curve. That's a lot. It's not all of it, but a lot. But I get ahead of myself. Anything past this point in either direction would be considered unusual, just as a kind of a threshold. Yeah. Any questions before we look at the formula sheet again? Okay. All good. Hey, we know how to read this now. If X follows a normal distribution with a mean mu and a standard deviation sigma, then we use Z, which follows a normal distribution, right? The shape is the same. We've just shrunk it down. Now it's centered on 0 with a spread of 1. Okay. Where Z, how do we get all our Zs? We take X minus mu divided by sigma. You don't even really need this part, in my opinion, because what is that? That's just solving this little guy for X. Z is X minus mu over sigma. You're going to multiply sigma over Z. Sigma is X minus mu. Then you're going to add mu to both sides. Z sigma plus mu is X, but that is just this rearranged, right? Mu plus Z sigma. So you don't really need the second one, but it's on there because we're going to be working, I call it backwards or forwards and backwards, but we're going to be solving for Z. And then we're going to be given a Z and solve for X instead. Right. So that's what we're working towards. But this is this formula here. So like I said, you don't really need it. Now, some properties of Z, bless you, and any normal distribution, but Z is the one we're going to focus on, is probably outlined pretty thoroughly in the slides, but let's write it out together so that it feels more official. It is important. Okay. Z scores some facts. Or Z score facts, let's call them that. Wait. First, Z follows a normal distribution. 0, 1 means what? Z follows a normal distribution, and I'll capitalize it because it's a name, but you don't have to. Follows a normal distribution with a mean of 0 and standard deviation of 1. That's a good first fact. Okay, we've got the shape, center, and spread. We can sketch this out. leading us to our second fact, which is that a z-score that's negative, right? Those are values that are below the mean, right? And so the second fact is that negative z-scores are below the mean. And vice versa, positive z-scores are above the mean. We've already seen that, but it's nice to have it all kind of laid out for us. What is a z-score? So the z-score, it tells us how many standard deviations above or below the mean it is. So let's do z equals x minus mu over sigma, right? The z-score tells us how many standard deviations sigma, I'll put in brackets, right? An observation which is x is above or below the mean, which is mu. Oops. Okay. That's good to have up our sleeves, right? Because then we know that it's essentially unitless, right? It's the number of standard deviations above or below the mean. So if you can standardize values and compare them, then that's great. How about a fourth fact? We can fit 3 standard deviations, and this is for any, and maybe what I should do is any moving on to normal distribution facts. Not just Z, although Z is and follows a normal distribution, so it does apply to Z as well. Okay. And so now we're kind of graduating to any sort of normal distribution. First fact, for any normal distribution, we hinted at it, we can fit approximately 3 standard deviations on either side of the mean before we kind of run out of curve. We can fit roughly 3 standard deviations on either side of the mean I'll do it on this page. That's a fact. Why do I say roughly? Because the next fact is, I know, how are you supposed to know? These tails, they go from negative infinity to positive infinity. So in theory, these tails, the tails continue out to plus minus infinity. Which is kind of mind blowing. In theory. Obviously, you can't be negative infinity tall, but in theory, we're allowing for it. Okay. And so here, if I have mu, then this keeps going to negative infinity and it keeps going to positive infinity. Okay. But the majority of the curve kind of gaps out here at mu minus 3 sigma and mu plus 3 sigma, right? Moving out 3 standard deviations on either side, we've captured the majority of the curve, but it does keep going, right? But how are we going to use these areas? These areas under the curve are probabilities, right? And so the area under the curve is a probability. What do we know about probabilities? Recall the probability of the sample space is 1. I know. Thought we were done with that, Emily. We are. But that's kind of root knowledge that we need to have. What does the sample space look like in this case? All possible outcomes still, right? But now we're on this continuous scale from negative infinity out to positive infinity, which means that the total area under the curve is 1. Okay? And so therefore, the total area under the curve, is 1. We're going to use that quite a bit. Knowing that the total area under the curve is 1. Now, I always kind of find it mind-boggling, right? If this thing keeps going and going, notice how I didn't close the gap here. It just keeps going and going and going and going and going and going and going out to negative infinity, positive infinity. That means it never closes. And still somehow the total area is 1, right? And so that's kind of wild to think about, in my opinion. But that's just how it is, right? And so, and we can use calculus to show that that's true, but we don't need to, right? But we can then use the fact that the area under the curve represents probabilities, and knowing the total probability is 1, right? Then what can I do? I can slice and dice this thing into areas that I want to find the probability of. Okay. I'm going to highlight this one. I made it number 3, but we had to get there. But that's how we're going to use these z-scores mostly, right? And so what we're going to do is we're going to use z-scores to find areas under the curve, which means finding probabilities. Okay. Anything else I wanted to say here? We use z-scores to find areas under the curve. Oops. Which are probabilities. Okay. Because remember, Z Z is centered on 0, has a standard deviation of 1, right? So now all of a sudden we have this kind of nice looking curve that we can shrink all our other curves down to, right? We don't need to know what I can't even come up with examples. A normal centered on 19 with a standard deviation of 2 looks like, versus a normal with a mean of 19 and a standard deviation of 3 would look different, right? And so if we just standardize all our values, then they're all going to be on this standardized curve. But mapping out the other facts, right? -1, -2, -3. Notice that I leave some room there. It's tiny, but that's okay. 1, 2, 3. Okay. Keeps going. There is space there. But what does a tiny space mean? The area under the curve is the probability, right? And so here, the area under the curve is a probability, and so this indicates a very small probability. So that's how we're going to use these things. So from some observation X, you're first going to calculate a Z by taking Z equals X minus mu over sigma. Right? So X is going to have some mu and sigma. And so then you can standardize it to calculate your Z. Now you're on this beautiful curve, same shape, right? But different center, different spread. And then notice how I haven't said how we find those probabilities, but then you glance down and you see this table. Oh geez, this is probably how it is. Spoiler alert. So if you don't have a table yet, you'll need it. And so then we're going to be able to find a probability using the table. And then what we're building up towards is, okay, so if I give you some observation, you can find some probability, but it's going to be kind of a two-step process, right? First, you have to standardize it, and then you have to find the probability. Okay. Or an alternative that we're going to work towards is I give you a probability, then you need to backtrack, but you use the table to backtrack to Z, and then you can find your X, right? To find the observation associated with some probability, right? Okay. There's so much to say, but I know it's on all the other slides, so I'm trying not to. All right, that's probably good. Any questions about those before we? Okay. Percentiles, we've seen percentiles before, right? 5-number summary, we had to find Q1, Q3, the median, right? Those are percentiles, but a percentile in general is the percentage of observations that fall below a given data point. Okay. So here, if we have a percentile, right, then a percentile is the percentage or probability, right, or proportion. Remember, they all mean the same thing still. Okay, so here you see percentage, but you're going to think, well, roughly, that's roughly a proportion, which is a probability, right? P, all those 3 P's still mean the same thing. They'll continue to mean the same thing. So if I know that the area under the curve is a probability, well, then it's also some percentage of the population that satisfies some criteria or some proportion of the population that satisfies some criteria. In this case, this shaded area is the proportion or the probability of having a score of up to and including 1800 on the SATs, I think. Looks like Pam's score. So this area is the probability, oops, of a score less than 1800. I'll say it, this is the SATs on the SATs. Okay. So this area is what we're working towards being able to find, right? Because we want to know what's the probability of a score less than 1800, or maybe more interesting, what's the probability of scoring higher than 1800? What do we leverage then? Well, if I know that the total area is 1, and I know the area to the left is 0.8, let's call it, what's the area to the right? Must be 0.2, right? Complements. We don't call them that. We know what they are. We use them already, but right, and so that's how we're going to leverage this. Okay. We use Excel, not R. But there's a norm.s.dist command that takes your Z, and we're just always going to do true. Cumulative equals true. Obviously, there's an Excel assignment coming your way on working through that. This is the first time where I'm going to introduce Excel in class. The other ones, I did get some questions. You haven't done this in class. I know. They're standalone. Because Excel is not on the test, right? It is a life skill that I think we all acknowledge that we should probably have, right? Or have an idea of how it works, but it's not on the test. And so for some of those, you know, they're just knowledge that you can have. They're weighted the same. Oh, that's another thing I forgot. I had promised you guys 15 late passes. I don't know if you can see how many you had, but you only had 10. So that was pretty rude of me. So I bumped those up. Everyone just, you get a late pass, you get a late pass, everyone. So now if you haven't used any, you have 15, or if you use some, you have 5 more than you had before. So, and those Excel assignments just get lumped into your assignments, right? So they're not worth very much because we do a lot of assignments. But we're not ready to introduce the Excel because we don't know what it is yet. But we will have an Excel command that just does it and finds the exact value under the curve or the exact area under the curve, right? And so that's nice. There's lots of online calculators. And whenever you're using Excel, things change. And so I wrote those instructions, I guess 2 years ago now. And so maybe there are instances that I'm finding where it's kind of, they've changed the process. So maybe my instructions are not exactly bang on, but if you're finding that, you can just Google it. Google it. Rude, I know. Okay. So there's lots of applets and online calculators and things that we can use. And here we will use, I'm gonna call it the T table instead of the Z table. Guess I shouldn't put the T table in quotes because it is what we're using. Hey, why, undo. Undo. There. This is the Z table. Very, very archaic because what does it do? This table is also very archaic, outdated. If you go into the workplace and you have to do a calculation like this, and then you just say, wait, where's my table? They'll laugh at you, obviously. But we need it for our tests because we don't have software in the test. So for us, we do have to use this kind of ancient way, but we have calculators and software that do it for us. And so that's why it's important to know how to do it in Excel, right? But for developing the general idea, I'm going to cross this out and I'm going to bring in the table that we have instead, which is, where do we think? Maybe, well, I know. How are you supposed to know? Here's a copy. Copy. Clearly, I have many copies of this thing. Hey. Copy. And I'm gonna add a page, or sorry, paste. You can't see what I'm doing and it kind of drives me bonkers actually. I need you to see me struggling. So this is the table. We will use this table. Kind of eliminating some paper, some printing, because we can have the same information. Okay, for us, all we're gonna use until we get to chapter 6, I think, is this, and these little guys. So until way later, you can ignore everything else. What's nice about just starting in this table is we apply the same technique when we move into T's, which behave slightly differently. Okay, so we're going to work with Z's and T's eventually, but oh, I shouldn't have done this, should I have? Gonna copy so I'm not scrolling constantly. Eek. Can I get these to line up? Maybe not. Hey, pretty good. So this, just ignore these. Obviously, you can see that it continues up, 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 but I'm going to save this as one image. Copy, paste. Let's do it over it. There. Good enough. So for now, this is all we need for our probability findings. Okay. Now, what does this look like? The only thing we probably recognize so far is the Z. It's called Z star in this case, but it's just a Z. So Z is Z star. Notice that these guys are all positive. Okay. And so we know what Z looks like. Let's see if I can make it nice and big here. Z looks like this, centered on 0 with a standard deviation of 1. Here, we have a Z of 0.674. I'm gonna pick some go-tos here and do different colors. And sure, pink here. Because if we do 3, the rest of them just kind of fall into place, but it gets really tight, right? And so what do I mean by tight? Well, if I have on a number scale, so remember, this is just a number scale, and I have 0.674, right, a Z of 0.674. What this table is telling me is that if I go up here this way, the one-sided P is really the one-sided probability. Okay. So one-sided P, where P is the probability. Okay. And if you've taken a stats course before, then you're probably used to using the Z table, which is fine. But we're doing the same thing. But the one-sided P at Z equal to 0.674 tells me that the area in the tail is 0.25. Okay. So how I indicate that, instead of shading, so technically this would all be shaded, and I guess I'll shade it for, let's do something kind of cute, like, wait, not so cute. So that area, we're told, is 0.25. What's one of the things that we know about the normal distribution is that it's symmetric, right? In fact, it's going to be symmetric about the mean. And so what else do we know here? I can go down to negative 0.674. So at Z, negative 0.674. And by symmetry, kind of wonky, but by symmetry, I should have the same area in the tail here, 0.25. Right, by symmetry. And I'll try to do kind of cool like that. So knowing the positive version, I also know the negative version because it behaves the same, right? So we really only need half the table. Okay. If we looked at the Z table, there's a negative and then it goes to a positive version. This is just a more condensed way of looking at it. Okay, so how can we use this? So now, what does this mean? The probability of being negative or 0.674 standard deviations below the mean, because it's negative, the probability of that is 0.25 or 25%, right? Or the proportion of observations less than 0.674 standard deviations below the mean is 0.25. Then we can ignore the two-sided, because what's the two-sided telling us? We won't need that until we do hypothesis testing, but then we want both areas, but that's just 0.25 plus 0.25. There's nothing kind of groundbreaking here. 0.25 times 2 is 0.5, 0.2 times 2 is 0.4. You really don't need that second line. It's nice to have it, but 0.15 times 2 is 0.3, right? And so you can kind of ignore that bottom line for a little bit. But how can we use this? So for example, what is the probability a score is within plus minus 0.674 standard deviations? I'm using 0.674 because it's the value that we have. We're going to move away from that. But what do we want to find? That's this area, right? Remembering that probabilities are areas under the curve. How would you find that? You could say, well, I know the total area is 1. And I know, what if I lob off this 0.25 as well as this 0.25, I'm left with the area that I want, right? And so we leverage, so then the probability is 1 minus 0.25 minus 0.25, which is 0.5. There's like a glitch, but not on there, right? Just on my iPad. Good. All right. So then, okay, let's do the same thing, but let's move out a little bit, right? To a Z of 1.645. Hindsight. That's good. Okay. 1.645, let's draw is here, 1.645. Now I would draw a new curve, but I want you to see that they're all on the same scale, or all on the same line here. And so if we draw this line up here, we are told that the area in one of the tails is 0.05 or 5%. Right? And so here, which would be, if we were to shade the area, right, it's everything above here. But it makes it a lot cleaner if we just draw the line above, because often we're going to have overlapping areas anyways, and that just makes it really messy. And so that's why I draw these kind of arrows above to indicate the area in that direction. Right? If I know the area above is 0.05, right, in the tail, then by symmetry, what's that area? Or not by symmetry, I guess, by the total area is 1, right? This must be 1 minus 0.05, which is 0.95. Right. Okay. So each of these, they're just little check-in points that we can use. And how about 3.091? Let's put it out here. Has an area in the tail of 0.001. Very, very small. You don't want to miss any zeros there either. By symmetry, that means that also on this side, I can go to negative 3.091. And the area in that lower tail is also 0.001. Oh, I did it wonky, didn't I? Why is it wonky? This one's all short and this one's all tall and they should be symmetric. Oops. Let's see if I can. Oh boy. I can't move it. I'll just make it worse. They're supposed to be symmetric. Okay. It's okay. Right. Can draw one for the green too, because they're the same, negative 1.645. See if I can. Now this area is 0.05, which means on the upper end it's 0.95. What if you have Z scores that are not in one of those values, right? What if Z, like as an example, like, what is the probability of Z greater than 2? Okay. What are we going to do? We're going to take a Z of 2 and we try to place it somewhere along here. Notice that, of course, as I move out from 0, right, it's just increasing this way. And so if I place 2 somewhere in here, 2 is somewhere between 1.96 and 2.054. Fair enough. Right. So let's see here. What does this look like? Z is centered on 0 with a standard deviation of 1. And I have a Z of 2 that I'm interested in. Now from the table, oh, what's another thing I should be writing down here? If I want to find the probability, no, well, actually that is useful, but not yet. Keep it up my sleeve. If I'm asking for the probability of being greater than 2, the probability is the area under the curve, and 2 is my cutoff, right? So really what I want is I want to know what this area is, right? So the area above 2, or Z equal to 2. We don't have 2, but we know from the table. So from the table, and this is when I'll bring it in here. I see that 2 is somewhere between Z equal to 2 is between 1.960 and 2.054. You can write that out in words if you want, right? I'll use inequalities because it's a lot shorter, and the quicker we get used to it, the better, because we will be using the same notation essentially for the rest of the course now. So we'll get used to it, right? But Z equal to 2 is somewhere between a Z of 1.960 and 2.054. So now, what can I do? I can say, okay, then I can trace these up here. These are just for visualizing. So you don't need to think about kind of how close they are to each other. Just give yourself enough room to see what it is you're mapping out. Okay. And so, of course, both of these 1.96 and 2.054 are going to be very, very close to 2, but I'm giving myself enough room so that I can kind of see them. So 1.96 has an area, a one-sided P, or an area in the tail of, let's see here, 0.025. So I can write 0.025. And how about 2.054? Let's draw that out here. .054 has an area in the tail of 0.02. We wanted to find this area. Using this table, it's a little unsatisfactory just because we're just left with a range. But if I tell you that the probability is somewhere between 0.02 and 0.025, that's pretty good. Right? That's narrowed down, I think. Right? Narrowed down enough. Right? We'll use software to figure out what the actual value is. Right? But this probability is between 0.02 and 0.025. You want to be really careful that you read the smaller one first and then the bigger one, which is kind of reading right to left, which we're not used to, right? But if you just kind of take a step back and say, okay, well, this is my lower end of the probability and this is my higher end of the probability, it's going to be somewhere in there. And that's good enough for government work. It's good enough for us. So we'll use software. One thing about software though, should we do it? Should we just see what the actual probability is? I'll walk you through it. But a note on Excel, Excel only returns the area to the left. But what we can do is we can use equals norm.s.dist. The .s just means that we've standardized it already, so we're feeding it a z. There's other options that we can use where we just give it the x, the mu, and the sigma, and it calculates z in the background. But z, and then we're going to use cumulative equals true because cumulative means up to and including 2, right? If it's false, it's just at 2, but we know that that should be 0, so we don't use that. Okay, where's my Excel? Here. You see that? Yeah. Okay. I want equals I'm not very good at norm. Even if you can't remember what you were gonna do, right? You can click through these information boxes, right? Norm.dist takes an X, a mean, and a standard deviation, and the cumulative command. And you can click on it to see a more elaborate instruction or more elaborate explanation. But we're going to use the norm.s.dist because it's already standardized. I'm giving it a Z. And so that's the one I want. And my Z is 2. And then always cumulative equals true. And I'm going to remove those brackets there. Happy, check mark. Okay. The area to the left, but what can I do? I can reference the cell. I can say equals 1 minus, right? Because we've got a total area of 1. Oh, this is not something I'm used to. Minus this guy. I get 0.02275. Now, I'm going to take a screenshot of this and bring it in. Whoa, sorry, guys. Cancel. No, think. So here, this is the area to the left. And here, what we did, this is 1 minus A1. Which means that the exact area to the right, we're told, so therefore, the area to the right is 0.02275. How does that compare to what we said? Well, all we were able to say with the table and on a test is that, okay, it's somewhere between 0.02 and 0.025. Notice that this is a slope, so we can't just go halfway between them because that's not how areas work if there's a slope, right? And so you want to be careful of that, but from the table, the probability is somewhere between 0.020 and 0.025. Are you convinced that 0.02275 is between those two values? Yay. I'm telling you, you are. So you can find the exact value. I'll highlight this because the reason not in blue. That's crazy. One off. Right. This is the cell that's highlighted, and this is what's being done in that cell. Right. 0.02275 is somewhere between 0.02 and 0.025. Close enough. Right. And so for us, we just need to have kind of a rough idea of the probabilities. And so that's how we're going to use this table. Okay. Using the table requires a little bit of work, right? A little bit of practice to begin with. One thing I do want to highlight, because it'll come back. Uh-oh. have I done? It's frozen. It'll come back. I hit paste, but it's not doing anything. Nothing's happening. Uh-oh. Okay, undo. We were waiting for that. This one, copy. Come on. Paste. Hello. I'm waiting for a paste of the table. There. We'll do. An important note about the table. Because sometimes we'll find Z scores that are less than 0.674. But let's remember that there's an imaginary zero here, right? Because it's centered at 0, and so you're starting at 0. And so really, you could have a 0 here. What's the area to above 0? If it's split in half of 1.5, right? So then the one-sided P here would be 0.5. Right? The area in one of the tails is 0.5. The area in both the tails from 0 is 1. Right? So that's why they're not included on here, but they will come into play. So that's why I want to highlight those guys. And what about here? We also know that Z, the curve, continues, right? It continues not just past 3.29, but it keeps going to infinity, right? So at this point, what they said was, well, I mean, who cares? Once you're past 3.29, the next stop is infinity. That's okay, because what happened? They reached a Z of 3.291, and they found the area in the tail is 0.0005. That's very, very, very small, right? So at that point, who cares? It's highly unlikely. The probability is small, good enough, bless you. And even in two tails, it's very small. But I often get frantic questions. Emily, I found a Z score of 12. I don't know what to do here. That can happen. Unlikely, right? Because the probability is so small, but it can happen, right? But 12 is somewhere between 3.291 and infinity. So what's the area at infinity? The area in one of the tails, this is where it gets weird, is 0 at infinity. Once you get to infinity, which you never will, the area past that is 0. Fair enough. Double that, still 0. And so these are kind of troublemakers because they're not on the table, but you can put them there, kind of imagine them being there. Okay, so that's really important to have that full table. And then you've got all the options, right, for all the ones we care about. It's not important really, but you may have heard of Six Sigma, which is a business process kind of idea. So 6 sigma, remember, so underneath the curve, we can move out 3 standard deviations in either direction, making a total of 6 sigma, right? And so if we move out 6 sigma, then virtually no items will fail to meet specifications, and so that's a good thing. We'll start with this example, but I want you to try it before Thursday, but we'll start here. So try on your own. And a note to myself, start here on Thursday. But it's too big to start now, but you can do it. So we'll end here, but you're welcome to try it. If you have any questions, let me know. Otherwise, I'll see you on Thursday.